Alright, so in this video I'm gonna be explaining an important article with the title Gated Domain Units for Multi-Source Domain Generalization. So this term says that our target is unseen target. It means that we are not even using the samples of the target. So this paper in 2023, the phenomenon of distribution shift occurs when a dataset at test time differs from the dataset at training time, which can significantly impair the performance of a machine learning model in practical settings due to a lack of knowledge about the data's distribution at test time. To address this problem, we postulate the real-world distributions are composed of latent invariant elementary distributions across different domains. This assumption implies an invariant structure in the solution space that enables knowledge transfer to unseen domains. To exploit this property for domain generalization, we introduce a modular neural network layer consisting of gated domain units that learn a representation for each latent elementary distribution. During inference, a weighted ensemble of learning machines can be created by comparing new observations with the representations of each elementary distribution. So this is an illustration of elementary distribution and the concept of gated domain units. While data sources are often considered as domains, for example, each hospital here is just one domain. Hospital 2 is domain 2. Hospital 3 is domain 3. We can depict examples of these subsets, latent domains, in three different shapes: rectangle, octahedron, and circle, for each domain, following the method of 2020. In contrast to existing work, the invariant elementary distribution assumption advocates that these latent domains remain invariant across the hospitals. Therefore, we propose to learn representations of these elementary domains akin to mixture models. So our latent domains are we have them in three different shapes. These three different shapes. For example, this one is circle. Just for illustration, they show it for different shapes. But they use gated domain units. And you see that P sub j is the j single source distribution for the source, but P sub j sub e is the j's elementary distribution. So E here stands for elementary, S for source. Each of the source datasets is assumed to be IID. So this is a visualization of invariant elementary distribution assumption for domain generalization. Both observed and test time distributions are composed of the same set of unobserved elementary distributions that remain invariant across different domains. Hence, the first challenge during training is to extract these elementary distributions from the observed data. The unobserved elementary distributions are represented by the elementary bases V sub 1 and V sub 2. The second challenge during inference is to create a weighted ensemble of learning machines that utilize the similarities between the embedding of unseen observations and the embedding of these distributions in. I have a playlist on reproducing kernel Hilbert space. So what is Pareto invariance? The IED assumption implies the invariant structure in the hypothesis space that can be exploited during training. So this is a definition of Pareto optimal. I have a playlist for multi-objective optimization that I talked about this Pareto optimal set. So if a hypothesis in there, suppose that IED assumption holds, for example, there exist k elementary distributions such that P of source is just a linear combination of your elementary distributions for some weights alpha. Then the corresponding Bayes predictor is Pareto optimal. Because now we are sampling from this source, which is a linear combination of these elementary distributions. And we employ the kernel mean embedding to represent the elementary distributions. The final prediction layer consists of three main components: a similarity function, defines under reproducing kernel Hilbert space that is shared across GDUs, elementary bases V sub j, and learning machine F for each elementary domain J. So you see the visualization of the layer, the upper panel, and its main components. The GDU, which is the lower panel, the layer consists of multiple GDUs that represent elementary distributions. During the training, the GDUs learn the elementary domain bases V1 till V sub m that approximate these distributions. In summary, the GDUs leverage the invariant elementary distributions and the assumption and represent our algorithmic contribution. The elementary domain bases, these V sub j's, are stored as layer weight matrices. So these are layered weight matrices, thus allowing us to learn them efficiently through backpropagation and avoid the dependency on problem adaptive methods like domain adversarial training and domain information. So we consider two geometry-based similarity measures for gamma. So we use cosine similarity and maximum mean discrepancy. To ensure beta sub ij sum up to 1, we apply the kernel softmax function. And for MMD, maximum mean discrepancy, we choose this edge. When given a batch of samples, we can compute the similarity between the batch with each domain basis by replacing phi of x tilde with the mean. Besides geometry-based similarity, we can also seek for an optimal projection of phi onto the span of these means, such that the distance between the phi and beta mu is small. Note that as a subspace H sub m, which is a span of all mu, are learned during training, we could incorporate pairwise orthogonality constraints that they are orthogonal. This is our constraint. In order to maximize the representation power of this subspace. So given a distribution, the mu is in span of this mu such that they are orthogonal, and the value of this sum is minimized by just so solution of that is this beta star. Then our learning objective is formalized as this. The goal of training can be described in terms of two components. Consider batch of training where B is the batch size. During training, we minimize the loss function for an underlying task and respective batch size. In addition, our objective is that the model learns to distinguish between different domains. Thus, the regularization, this term is the regularization is introduced. So we have this regularization to control the domain bases. So we require regularization to ensure the KMEs of the elementary domain bases are able to represent the KMEs of the elementary domains. Therefore, we minimize the maximum mean discrepancy between the feature mappings and the associated representation. So in the case of projection, the regularization is this. And sparse coding is an efficient technique to find at least possible basis to recover the data subject to a reconstruction error.